about rational expressions. Rational expressions are algebraic expressions as fractions. So if we think about it, we're going to have variables in the numerator and variables in the denominator. Our next unit is all about rational expressions. So before we get into the operations on rational expressions and solving rational equations, let's talk about some of the properties. The first most important property of a rational expression is its domain. Domain we know is the set of inputs. Which is often the variable x, but what that means is it's a set of x's that we can plug into that expression and have it simplified to a number, a real number. When we're finding the domain of a rational expression, we need to exclude any values that make the denominator equal 0. These values that make our denominator equal 0 are called the restrictions of the function. When we find domain for a rational expression, it will start as a restriction, and then depending on the question, we might go one step further to express our domain in interval notation. Find the domain of the rational expression, write your answer in interval notation. X squared plus 1 over x minus 6. When we're finding domain, the only part of the rational expression that we're concerned about is the denominator. So where does x minus 6 equal 0? We can solve this equation by adding 6 to both sides. So this value, x equals 6, actually represents our restriction. X cannot equal 6. Because if we were to substitute this value into the original expression, we would have a denominator of 0, which is undefined. So in red here, we have our restriction. So anytime a problem says state restrictions, this is what you do. X cannot equal whatever value. But since this question is asking for the domain in interval notation, we're going to go one step further and set up the interval that represents all the solutions that x can be. Now, with writing an interval, as we've seen in previous lessons, it's easier if we start with a graph. So if I set up my number line, here's 6, and 6 represents the value that x cannot be. X can be anything else, though. Since our graph has two different shaded regions, that means our domain is going to have two separate intervals. The first interval on the left, reading from left to right, goes from -infinity all the way to 6. But it does not include 6, again, because we're saying x cannot equal 6. Our next shaded region, reading from left to right, begins at 6 and ends at +infinity. And this is our domain in interval notation. Both of these statements, whether we choose to use restrictions or write our domain in interval notation, imply the same thing, but you have to be mindful how the question is asking you to submit your answer as to whether or not it's acceptable to use a restriction or if you have to use interval notation. 5x plus 4 over x squared minus 3x minus 10. Again, to find domain, we want to know where is x squared minus 3x minus 10. Where does this equal 0? To solve this, we want to factor our quadratic. Since we just reviewed factoring in our previous lesson, this should be pretty quick. Since our lead coefficient was 1, we jump straight to our two binomials. Factors of -10 that sum to -3, -5, and +2. Now the zero product property tells me that if I've got two things being multiplied that equals 0, then either x minus 5 equals 0 or x plus 2 equals 0. So the solution to this equation is x equals 5 and -2. The solution to this equation happens to be the restrictions for my rational expression. Now I've got two restrictions. I'm going to set up my number line just like I did previously so that I can write my domain in interval notation. So here's -2, here's +5. I'm going to put some red circles around those because those are the two values that we cannot plug in for x. Everything else is fair game though. Any other value in those shaded regions, we can substitute into that expression and evaluate it. Since we have three separate shaded regions, we have three separate intervals for our domain. The first one goes from -infinity to -2. This middle one starts at -2 and goes to 5. And the third one begins at 5 and ends at +infinity. Now, the more restrictions we have, obviously our domain in interval notation is going to get quite lengthy. So if we have a lot of restrictions, typically speaking, we're just going to ask you to state the restrictions instead of using interval notation to represent your domain. x² minus 9/4. The only portion of our rational expression that we are concerned with for finding domain is the denominator. So we have this. Where does 4 equal 0? Some red flags are going off because 4 does not ever equal 0. So there's no solution to this, which means that there are no restrictions for this rational expression. If there are no restrictions, then our domain is all real numbers or -infinity to +infinity. Now that we understand a little bit about domain, let's look at simplifying rational expressions. Think about when you first learned how to deal with fractions, you learned the most important thing is that whenever you have a fraction, you have to simplify it. Well, a rational expression is just that, it's a fraction, so we have to simplify it just like we would with a number, but it requires a little bit more finesse because we've got to factor algebraic expressions. 3y cubed divided by 6y to the 4th minus 3y cubed. We're going to start by factoring the numerator and the denominator. Factoring the denominator is going to help us simplify, but also it's going to help us better identify what our restrictions are. So our numerator is going to stay the same, 3y cubed, but in the denominator, I have a GCF of 3y cubed. When I factor out 3y cubed from the denominator, I'm left with 2y minus 1. Here we can find what our restrictions are. What can y not equal? If you need to set up your equations in your margin, 3y cubed equals 0, 2y minus 1 equals 0, you can do that and solve those little baby equations in your margin. It'll help you make sure that you have the correct sign and the correct placement of your values. If you can just see the values, then that's fine as well. From here, we get that y cannot equal 0. From this second equation, we're going to get y cannot equal +1/2. So here are our restrictions. And now that we've stated restrictions, we can start simplifying like factors. If you look in the numerator and the denominator, notice we both have a factor of 3y cubed. So 3y cubed divided by 3y cubed is really just 1. When we multiply across or when we look at our final answer, we just have 1 over 2y minus 1. And we maintain our restrictions, y cannot equal 0 or 1/2. Sorry, guys. There it is. I must have hit the up arrow. 5x squared minus 6x plus 1 divided by 3x squared plus 4x minus 7. Again, we're going to get a lot of practice on factoring. I want you to go ahead and pause the video right here, factor the numerator and factor the denominator using whatever technique you prefer, and then go ahead and press play, check your factors with mine. All right, if you've come back, the factors for the numerator are 5x minus 1 times x minus 1. And in the denominator, we have 3x plus 7 times x minus 1. Now that everything is factored, we want to state our restrictions. Setting both of your factors in the denominator equal to 0, we get x cannot equal negative 7 over 3, and x cannot equal positive 1. Now that we've stated our restrictions, now we can start to simplify like factors in the numerator and the denominator. We can see that both the numerator and the denominator have a factor of x minus 1, so they cancel each other out. And our final answer is 5x minus 1 over 3x plus 7, where x cannot equal negative 7 over 3 and positive 1. This is our simplified rational expression. Five minus x over x minus 5. At first glance, these two expressions in the numerator and the denominator look very similar, but we know that they're not the same because subtraction is not commutative. Think about the following. 2 minus 3 is not the same as 3 minus 2. So 5 minus x is not the same as x minus 5. But there is a trick here, and this trick, once you've been taught it, is pretty easy to identify. Because those are very similar, what we want to do is we want to rewrite all of our terms so that the variable comes first, or excuse me, all of our expressions so that the variable comes first. So if I look at my numerator, if I want to make the variable come first, this is negative x plus 5 divided by x minus 5. I just changed the order. Now, if you recall from our video on factoring, anytime we have a lead coefficient that's negative, that's something that we want to factor out of the expression. So if I factor a negative 1 out of my numerator, we have negative 1 times x minus 5. Negative x divided by negative 1 is x. Positive 5 divided by negative 1 is at negative 5. And this is divided by x minus 5. So again, we've completed our factoring. Let's state our restrictions. X cannot equal positive 5. And now that we've stated our restrictions, we can simplify any like factors in the top and the bottom. Those are the x minus 5s. So this original rational expression simplifies to negative 1. But we maintain those restrictions. X cannot equal negative 5. That seems a little strange since we no longer have a variable in our expression, but remember that simplifying doesn't actually change our expression, it just changes the way it looks. So this negative 1 is still representing that original rational expression, and that original has a restriction that x cannot equal positive 5. 3 minus 3x squared divided by x squared plus x minus 2. Again, let's start by factoring everything. We can factor out a 3 in the numerator, 1 minus x squared, divided by x plus 2x minus 1. Now, 1 minus x squared, you should recognize at this point that this is a difference of two squares, but be careful of the order. Now the 1 is your a and the x squared is your b. So when we factor this actually factors to 1 plus x times 1 minus x divided by x plus 2 times x minus 1. Now we recognize these two terms, these two expressions are very similar. They're subtraction problems in a different order. And we always want our variables to come first. So what we're going to do is we're going to rewrite this second factor in the top, 1 minus x, as negative x plus 1. And actually, I'm going to do that for both of them. 1 plus x, I'm going to rewrite as x plus 1. And I can change the order just fine with that because addition is commutative. This second one is negative x plus 1 divided by x plus 2 times x minus 1. Again, I'm still in that factoring step, so I haven't started stating restrictions because everything is not completely factored. However, since our denominator doesn't seem to be changing at all, you could have already stated restrictions if you wanted to. Now from this factor, that lead coefficient is negative, so I want to factor that negative out. When I factor that negative out, it's actually going to come to the very front, so this becomes a negative 3 times x plus 1. And I factored the negative out of this, so I'm going to be left with x minus 1 divided by x plus 2 times x minus 1. I'm going to go ahead and state restrictions over here to the left. Looking at my denominator, x cannot equal negative 2, and x cannot equal positive 1. And now that I've stated restrictions, I can start canceling out like factors. Here now this x minus 1 and this x minus 1 are the same, so they cancel each other out. And it doesn't look as though anything else will cancel out. So we're done. Negative 3 times x plus 1 divided by x plus 2, where x cannot equal negative 2 and 1. Again, if I haven't mentioned this, I'm mentioning it now. If I have, sorry. You don't need to distribute that negative 3. You can keep it factored. Same thing in the denominator. If you have multiple factors in the denominator, you can just leave it factored, okay? Okay, so again, to recap, domain, you're trying to find the restrictions. Those restrictions are the values that make your denominator equal 0. Now, make sure that you read the directions. Sometimes it's sufficient to just say x cannot equal whatever the values are, like we saw in the last couple examples. Other times, they want the domain in interval notation. We saw that setting up our number line and circling our restrictions made it a little bit easier to identify the interval notation for the domain. When you guys are simplifying, you start by factoring everything and then make sure that you state all your restrictions. Your restrictions are going to carry through the rest of the problem, so we want to make sure that we state them at the very beginning. Then we can cancel out any like factors and then simplify from there, making sure that you keep all those restrictions you had. In the next video, you guys are going to look at multiplying and dividing rational expressions, which builds off of what we saw in this video. We'll see you then. Thank you.